Okay, welcome everybody. Thank you for joining me. Today's topic is Unit 1, Anatomy Unit 1, Learning Outcomes 7. So it's the energy systems. There's two pages worth of work to complete for this. And I just wanted to sort of give a real overview of the topic, dig deep a bit, and then in the last few slides, I'll kind of show a kind of plan and an organization you can use to complete the work. So without further ado, let's get straight into it. There's some bits I'll zip through quite quickly, um, but you've got this recording, so pause it at any time. I do also encourage you to make use of the course manual as well. So I would encourage you to when guided to do that, to have a quick read just to try and sort of double go over it a couple of times. So let's crack on. So by the end of the session, the aim of the session is to understand energy systems and their relation to exercise. So really useful for, particularly when we're planning with clients, it's useful to know what activities they're doing, what energy systems they'll be using, so that we can work to try and enhance those energy systems. So by the end of this session, you'll be able to describe how carbohydrates, fats, and proteins are used in the production of energy. So a bit of it is also going to look at the concept of energy, and how we can kind of relay that to clients, and maybe sort of refine the language that we use. We're going to explain the use of the three energy systems during aerobic and anaerobic exercise. So we'll sort of look at the different pathways, and what the sort of similarities and differences are in each system. Our energy systems. So our bodies require energy to do a lot of things. From our perspective, we're mostly considering about movement, but the body's energy currency, if you like, is kind of used for every cellular process. So wherever we take in our foods, our fuel, we use those fuels to provide our energy, provide our cells with energy for them to do their jobs. So some cells will kind of package proteins up and pass them into the body. Some cells will do sort of filtering and digestion, and they require energy. So our body uses energy in lots of ways, but what it uses as energy is pretty sort of universal. It's the same sort of thing. So our bodies use energy to provide movement, to produce force against objects, generate heat. We use it to grow and repair. But I'd also include things like digestion, absorption. Any cell that does anything. So every cell needs energy in some form. So we asked the question: what is energy? So you can find in your manuals a nice definition of what energy is, but essentially our energy, for our perspective, we'll look at more of a sort of movement sort of basis. Energy is required or is needed to allow our cells to perform work. So this could be our movements, our tasks within our body. So any cellular processes where things need to be moved, filtered, made, require energy. Particularly muscle cells require energy to contract. So this is where we probably have the biggest sort of control over the energy that we expel, or that we use, sorry, because our muscles are a big user of our energy stores. We see that because when we use them, we see these sort of byproducts of heat. So that comes from energy. That comes from our energy. The fact that as we move our muscles, we use energy to create the contractions, and byproducts of that is heat. It's a relatively inefficient motion. So cells and muscle fibers can't directly use their fuel. So if you think about what we eat, we only really get calories from carbohydrate, proteins, and fats. So water doesn't give us any calories, doesn't give us any energy. Everything else is made out of these: carbohydrate, proteins, and fats. So this is where we get off. This is our fuel, and we have to use that fuel to create an energy currency that our body can use. So to get there, we have to use very specific systems to convert our carbohydrates, proteins, and fats into this substance. So I asked the question, where do we use this energy? And I think it's sometimes almost just kind of is worth, even if we don't go in any great depth, it's useful just showing very briefly where energy is used. So here we've got a big muscle. So this is someone's forearm muscle, and we've just taken it apart. Now, as you look at this picture, you can see the connective tissue around the whole outside, which we looked at previously. And then we have bundles of muscle fibers here. And then we have an individual muscle fiber there. So we're starting to look at a microscopic level. So as you go to the next picture, we've got that at the top. We've got that muscle fiber, and sticking out, we've got little rods of protein. So here is one of those rods of protein. And what you can see is that we've got a dark bits there. And you can see in between these dark bits, I'm sort of roughly outlining, we've got a light bit. So when I look at the dark bit, this is what I'm looking at. So there's your dark bits together. Now, as you look even closer, you can start to see these little, I don't know what they look like. Well, they almost look like a team of rowers, don't they? Can you see that if you're looking on one of those big sort of team rowing boats from the top? They almost sort of look like they're gonna row. Now, if I look at that even closer, then what you find is that ATP is used in each of these individual points. Okay. Now, what happens is, if we imagine those little rowing boats, those little blue heads clip onto that little rope-like red structure and move it. They detach, they go back and move it. They detach, they go back and move it. So what you get is you get a drawing together of those two sort of red ends. So where I say red ends, I mean, I'm just going to draw it in. Just going to, there. Do you see that? That. And that. So do you see how the blue little rowing boats attach on? So those little rowing boats, the ones on the left-hand side are going to pull like so. The ones on the right-hand side are going to pull like so. So it draws those two ends together. So this is going to be pulled in that direction, and this is going to be pulled in that direction. So energy is used to do that pulling. So multiple times energy is used, the thing detached, energy is used, detached, energy is used, detached, energy is used, detached. So when we talk about energy being used in our bodies or being transferred onto anything, this is where it's happening at a very cellular level. So you can see at the top, we've got a little rod of protein. That little rod of protein is in this whole muscle fiber. If you go back a page, I'll try. If you go back a page, you can again see that muscle fiber there. A group of muscle fibers, a whole muscle. So that's where energy is used, at that cellular level. So we don't need to be able to recite that, but it's useful to just see where it's used. So we talk about this concept of us having an energy currency. So our energy currency is a substance called ATP. So ATP is used in muscle cells to power contractions. Now, ATP is a substance called adenosine triphosphate. Sounds complicated. So that is made up of one adenosine molecule plus how many phosphate molecules? 3 phosphate molecules. So three, adenosine triphosphate. So we have an adenosine molecule and 3 phosphate molecules. Let's have a look at what that looks like. So here is adenosine triphosphate. There's phosphate 1, there's phosphate 2, and there's phosphate 3, adenosine triphosphate. Now think of this as just a tiny, tiny molecule, minuscule. And think how many we're going to have, because if we think back to those previous slides, adenosine triphosphate is going to be used at every one of these little rowing boats, or every one of those little oars, every time they move. And so when they move, they're going to do it multiple times to create a contraction. So it's on a very microscopic level, tiny, tiny stuff. So adenosine triphosphate then is our body's energy currency. So where we have carbohydrate, where we have fats, where we have protein, in order for our body to use those fuels, it has to be converted into this substance, adenosine triphosphate. It's a bit like if you look at an oil rig, they bring out all this sort of energy-rich oil that's all sort of thick and black, and it gets transported to a refinery that has to make it into petrol. So to put petrol in my car, it needs to be very specific to my car. I can't just put crude oil in. So if we just sort of, we can't sort of inject protein, carbohydrate, and fat into our muscle and our body use it straight away. It has to refine it, use its energy systems to create this substance, ATP. So ATP, adenosine triphosphate, stores energy between the bonds. So basically, it's almost like if you can imagine if you release a champagne cork or, fizzy bottle of wine, it can fly off, pop off, it's an impressive sort of move. So that shows you there's stored energy inside that bottle. It has the capacity to pass that energy on to that cork so it can fly. It can also make noise. So that shows you there's energy inside that champagne bottle. In that adenosine triphosphate, the phosphates kind of are the corks. They screw that energy in. So what I want you to think of is, as that, let's have a look at this phosphate on the right. This phosphate here. So when that molecule was made, it had energy packed in between that bond. So if I uncork that phosphate, what's going to happen to that energy? Well, what's going to happen when this phosphate clears off is that it releases all the energy. So the release of that phosphate molecule releases that energy. So where do you think it's going to go? Well, a little bit of it's turned into heat. We know that because when we exercise, we get hot. But importantly, the place it goes to is those little rowing boats, those little myosin heads on our muscle fibers. So ATP releases energy for our cells to do work. ATP releases energy for our muscle cells to contract. So this is that process in close-up detail. I don't think we need to go through it massively, but it might be useful to just see. Remember I showed you those little rowing boats? This is them close up. This is those little blue rowing oars, shall I say. So the whole thing is, so these are the little oars I described. So if I show you back them quickly. So these little guys. So each one of those oars has attached to it a molecule of ATP. Can you see how that molecule of ATP is attached onto that little head? So I'm not going to go through the whole process now. It's quite a sort of, it's probably a level 3 thing. But essentially, what needs to happen is we need to transfer the energy in that whole molecule onto that little oar. So to do that, what you need is you need the ATP clipped on, and obviously we need to lose that phosphate molecule. That releases the energy and it gets transferred onto that little head, that little oar. So that's basically where energy gets used. We'll sort of we'll leave that one there. So your task now is to just read through your manual. So go to the manual for Learning Outcomes 7. This is on the muscular system. And I want you to fill in these gaps, okay? So I'm going to get you to just pause your presentation. I'll count you in 3, 2, 1 and pause. But I want you to spend a bit of time. Make sure you do pick up your manual because it's really useful for you to be able to then sort of recognize the terms that I'll talk with afterwards, okay? So if you can just do that for me, that would be great. So 3, 2, 1, pause. And so hopefully you did pause and had a go at it. So let's just have a quick run through this. So I'll answer. So ATP is the energy currency. 2 words used. So it's the energy currency of the body. There we go. Adenosine, ATP is adenosine triphosphate. ATP releases its energy when one of the, what do you think, phosphate bonds is broken, which causes energy to be released. There is enough stored energy in the body to provide only 2 or 3 seconds of energy. Once the body's ATP is used up, it must be, let's say, remade. There we are. Remade or resynthesized using the body's energy system. So the key thing is we have some in our body. We've got enough for about 2 seconds worth. So maybe enough for a golf swing, maybe a shot put. So not much. So importantly, once we've used that ATP, or to prevent us using it up entirely, we need energy systems to be remaking and reforming this ATP. So this is the sort of little poser question. ATP breaks off a phosphate molecule and gives its energy to the muscle fiber. We saw that. So what happens when we run out of ATP? Well, what's going to happen to the body? So hopefully you sort of think, well, we'll stop, won't we? We absolutely will. So we have to have systems in place that prevent that. So what we have is we have our energy systems. So these are our energy systems we're going to look at. So we're going to look at these 3 systems, and we're going to look at the concept of anaerobic and aerobic systems, but we're also going to have a look at the qualities of each one. So let's go through that now. So if we run out, or when we run out of ATP, we have to use energy systems to be able to continue exercising. So these are the 3 systems that we're going to work at. So where we've got to so far is here. So when we look at this, ATP we get is adenosine triphosphate. So we know it looks a bit like, that's an A, that's a phosphate 1, that's a phosphate 2, and I'll do a 3rd phosphate there. So adenosine triphosphate, there we go. 1 adenosine molecule in the middle, 3 phosphates attached. Where's the energy? Well, it's released in the bonds. So we need to lose that phosphate to release that energy. Let me get rid of that picture, it's terrible. So ATP is adenosine triphosphate, our body's energy currency. ATP is broken down to release energy for our cells. So we have to resynthesize ATP. And to do that, we can use one of 3 energy systems. Our anaerobic creatine phosphate system, our other anaerobic lactate system, and our aerobic system. So we'll look at the fuels, we'll look at the properties of each system, and give a little guide to completing your workbook. Okay, so first system. So the question I pose here is, so ATP breaks off a phosphate molecule and gives its energy to the muscle fiber. So the question really is asking what's left. So I just want you to pause that question for a minute. Okay, so the question is just to really have a think is what's left. So here you've got the phosphate molecule breaking away. You've got the energy has been released and transferred onto the muscle fibers. So we're actually just left with this thing. So if ATP was adenosine triphosphate, this is adenosine diphosphate. It's got 2 phosphates attached, 1 and 2. So have that in mind. We've got 2 of these phosphates left. So ATP becomes AD plus P, adenosine diphosphate, plus a spare phosphate, and also this energy that went to the muscle fiber. So energy has been, or the energy has been transferred to the muscle cells to power contraction. So the question is, what's the quickest way to reform ATP? What can you see if we've left with adenosine diphosphate, those two phosphates, this bit, what's the quickest way to make that ATP again? What's the quickest way? So the quickest way is actually to just add a new phosphate. So what we've got here, you may have heard of people taking or supplementing with something called creatine. Often people sort of think it's a sort of bodybuilding supplement. It's not really. It's to do with energy systems. So we left that last picture with this, didn't we? We had an adenosine and we had the two phosphate molecules. So now we're introducing a new substance, creatine phosphate. Well, there's the phosphate and there's the creatine. So creatine phosphate is another tiny molecule packed with energy, and what it allows us to do as beings is to create a quick release of energy. So let's just trace this along. Here we've got creatine phosphate. So we get it normally in our body. We can store enough of it for about 10 seconds of exercise. So when people supplement with creatine, they're trying to boost a store that is pretty limited anyway. It has some effect, but it's going to be, allow a tiny little boost. So for some people, it might allow them, a bit more power, perhaps. Maybe there's a sprint, maybe a little bit more intensely, but it's relatively limited. So creatine phosphate, what you can see, goes in this direction. Now, look at what's happened. The creatine molecule has separated. So let's just forget that for a minute. The creatine is no more. Now, what that's left, it's left a phosphate molecule and the energy it has with it. So we add those onto that adenosine diphosphate that we had left over. And so now what we've got is a fully reformed adenosine triphosphate. So the pictures could probably be much easier, but effectively you're starting with this and you're basically just donating that phosphate and its energy. So it becomes adenosine triphosphate. There we are. So it's really useful for high intensity exercise. It provides energy. You use this system when you work intensively. So as I'm sat here, I'm using mostly my aerobic system. It's the efficient way of me sat here on my behind. If I do, let's say, a couple of very sort of slow press ups, I probably still won't use this system. If I start sprinting down the road, I will start using this system. It's when my muscle contractions are really high intensity, this is when this system starts kicking in. So it's used in things like a 100-meter sprint. It will fuel a large amount of that race. If I serve in tennis and then have a quick rally that lasts less than 10 seconds, then this system is probably going to predominate, especially if it's a really high intensity point. So let's say I serve, follow into the net, boom. This system is the one that's using. If I serve very gently and just play the point out, just sort of, a practice hit, I'll probably use that system maybe for a second or two, and then start using my other, maybe more aerobic systems. So it's not like it's you once you're started using it, you use it for 10 seconds and then it's gone. I can use it for up to around 10 seconds. So something like a striker sprinting in on goal, let's say you're moving around, you're using your sort of aerobic systems, just jogging into position, and then someone puts a ball over the top, boom, you follow it into the goal, you're bearing down on the striker. The fact that you're running at that high intensity means that this system is the key one. So it's going to really predominate in those sort of instances. It's important to mention, so like I was trying to say with my examples, it's rare for a system to just be working alone. Even in something like a 100-meter sprint, the ATP PC system, or this creatine phosphate system, sorry, is going to be dominant, but you will also have got some energy from your aerobic system and also some from your lactate system. So it's going to definitely be the key system, but the other ones don't sort of switch off automatically. So that's the creatine phosphate system. There we go. So have a look at that picture. See what you can remember about that creatine phosphate system. How long does it last? What fuel does it use? What activities use it? So it lasts around 10 seconds. It uses creatine phosphate, and it's used in sprinting high intensity activities. So we're now going to go on to this next one, which is that lactate system. So let's press ahead. So this is the lactate system. In your books, you've got this nice picture. It would be worth actually digging into your books in a second. Before you do, I just want to sort of draw your attention to this. So this start point, glucose from glycogen breakdown or delivered from blood, it says underneath. It's a bit fuzzy. So this system uses glucose. Where do you get glucose from? Well, in our body, we store it as a substance called glycogen, which is our way of storing carbohydrate. So carbohydrate, whether you eat pasta, rice, potatoes, a Mars bar, some Haribo, have a can of Coke, ultimately that is all types of carbohydrate, and your body will use it as glucose. So glucose is the start point for this system. It undergoes a process called glycolysis. Anywhere where you see an olysis, it means a breaking down. So this is just a breakdown of glycogen and glucose, our body's carbohydrate. So what I want you to do is, I've got a little task. There we go. I want you to read your manual on the section on the lactate system. I want you to be able to answer me these four questions. So what is the fuel used and where is it stored? Is oxygen present when it's broken down? Tell me what the waste product is. And also tell me when lactic acid, that might be a hint for the previous question, when lactic acid becomes a problem. So I'm going to get you to read your manual and answer those four questions before we go any further. It's really important that you do take time to get in there. So I'm going to count you in and pause the presentation. So 3, 2, 1, pause. So welcome back. Let's press on. So the fuel used is glucose that circulates in the blood, or glycogen from our muscles. We also store glycogen in our liver. Oxygen is not present when it's broken down. This is the anaerobic part of this system. It's without oxygen. It means that we have access to the fuel very quickly, but in not a very efficient way. So we'll talk about the aerobic system in a while, but as an example, if I break down glucose using my anaerobic system, my lactate system that we have on here, I will get roughly 2 molecules of ATP as my net gain. You can see it there actually. So here, sorry. So you can see here that I start with a molecule of glucose, I undergo glycolysis, and the byproduct is 2 molecules of ATP. What comes out is first this substance called pyruvic acid, and if there's no oxygen present, that pyruvic acid becomes this substance at the bottom, lactic acid. So lactic acid is the stuff you know that will cause your muscles to burn and ache when we're working hard. Now, that 2 ATP gain, if I were able to use glucose aerobically through my aerobic system, which I'll show you later, I'd get around 38 molecules of ATP. So much more efficient. So this lactate system is another sort of, it's a quick energy system that does have byproducts. So the fuel that we use is glucose or glycogen. Oxygen is not present. The waste product is lactic acid. And lactic acid is a problem when it's released or when it accumulates. So we use this system quite a lot actually. We create lactic acid, it's allowed into our blood, and if we've got enough oxygen, we just clear it, we process it, it gets actually used in the aerobic system, we don't register it. If I work hard and lactic acid is being accumulated and I can't get enough oxygen into my body, then lactic acid begins to accumulate and accumulate until it reaches a point where I start to notice it. So I might start to notice it as that sort of burning sensation, and then ultimately it will stop me breaking down new fuel. So I'll start to get weaker muscle contractions. So lactic acid becomes a problem when it starts to accumulate in our muscles. So the system will provide energy when we're working hard, near maximal exercise that lasts longer than the creatine phosphate system can provide. So if I'm, let's say, doing a 200-meter race, the start is going to be really fueled. You know, the dominant system is going to be my creatine phosphate system, and then my lactic acid system is going to sort of be working in the background, and it's going to become really critical once I get past that sort of 80-meter phase. I'm also going to use it when the intensity of aerobic activity is too great for the aerobic energy system to manage alone. So if you imagine something like, let's say I was doing a 1,500-meter run, about 4 laps of a track, or just less than 4 laps of a track. Now, the first lap, I'm going to go pretty quick. I want to sort of, keep up with the others. But I might be able to do that mostly using my aerobic energy system. Now, let's say I keep going and people start pulling away from me, and I'm thinking, crikey, I'm in trouble here. So now I have to go that little bit quicker. And I can't produce energy quickly enough using my aerobic system. So my lactic acid system has to act like a little turbo and just start breaking down glucose anaerobically to meet my energy demands. So if I pace the race really well, I'll be able to see that finish line, maybe even the sort of, and pace it so my lactic acid system is just kicking in, just kicking in, just kicking in. So I'm using it, and then I only really notice it, let's say even in that home stretch. I'm on the last line, crowd are behind me, I'm running really fast. I can now feel that lactic acid, but I've paced myself perfectly so that lactic acid only accumulates in that last stretch. If I go out too fast, let's say I sprint the first lap, I'm going to get ahead of everyone, I will use my lactic acid system too much, and I'll have accumulated all that lactic acid, and I'll limit my sort of contractile ability for the rest of that race. So the lactate system converts carbohydrate, remember glucose and glycogen, into ATP. However, it also produces lactic acid, which is the byproduct. So lactic acid production is constantly occurring within the body, and it too can produce energy. So we sort of recycle it via our liver. However, should it start to accumulate in the muscles, it produces the burning sensation that you feel, which eventually forces you to stop. So in summary, the lactate system, it's a difficult one to say, right, it works only up to 1.5 minutes, which a lot of books say. If I was working all out, I would probably say yes, it will last up to 1.5 minutes with high intensity exercise, maybe even a little bit less. So the fuel is glucose or glycogen. I use it, it will dominate in really high intensity exercise, but I will start to use it in moderate to high intensity exercise to supplement the aerobic system. So it will last up to 1.5 minutes of intense exercise, but I can use it in longer duration exercises to sort of supplement my aerobic system. So it can be working for longer, but not at its maximum intensity. So an example might be a 400-meter run, a classic lactic acid run. So maybe the first sort of 60, 70 meters, it's going to be really sort of ATP PC system, with the aerobic and the lactic acid system kind of working in a little bit. And as that race progresses, the lactic acid system is really critical. Long rallies in tennis, when there's real high intensity, this system becomes really important. Where you've got a rally of say 20, 30 seconds, the lactic acid system is really critical. You see this because if people are particularly out of breath after the point has stopped, it shows you that system has worked, and now the aerobic system is clearing that lactic acid. That's why we need to breathe in so much. And something like a footballer running box to box at a high pace is using your lactic acid system. So lastly, the aerobic system. So aerobic means with oxygen and refers to the energy system which is able to produce ATP from the complete breakdown of carbohydrate and fat in the presence of oxygen. You can also break down a little protein as well when you're exhausted, or when you're exercising exhaustively. But carbohydrate and fat are the biggies. So when there is sufficient oxygen available to meet the energy production requirements, it is the energy system which dominates. So as I'm sat here on my behind, my aerobic system is working. I don't need to draw on my lactic acid system. I'm not producing any lactic acid. I definitely don't need my creatine phosphate system. If I walk down the road into the local town, I will be using my aerobic system. My fuel will be mostly fat. It's very low intensity. So this is especially true if the body's at rest. However, its use will increase as your cardiovascular fitness increases. since you're able to supply more oxygen to the muscles. So let's say I walk into town. That's very aerobic. I probably won't notice my breath increasing rate and depth much. It's a very easy exercise for me. If town was up a sort of 20% gradient and I needed to get there quickly, my walk, I'd start to notice my breathing rate start to be much harder. This would be using my aerobic system to a much greater extent. So where I'd walk in, I'd probably be using mostly fats as my energy store, or as my energy source. As I work harder, I start to use carbohydrate a little more as an energy source. And so the faster breathing shows that I'm starting to max out my aerobic system. If I then have to start running, my aerobic system is still working really hard, but I might now start to supplement it with my lactic acid system. So the fitter I am, the less I use that lactic acid system, the less I use my carbohydrates in that higher intensity exercise. So where does it all take place? Well, I want you now to just pause briefly to read your manual. So read your aerobic section of your course manual. And what I want you to do is answer these 4 questions. What does aerobic mean? What fuels are broken down? When is the system dominant? And what are the 2 main fuels used? And when would you use the other fuel? So just go to your manual, your course manual, and answer me those questions. So I'm going to count you into pause. 3, 2, 1, pause. So welcome back. I hope you paused. I hope you had time to look at your manuals. So the questions, I'll run through them very quickly. The question aerobics means with oxygen. The fuels broken down are primarily fat, which we use in very low intensity situations. So fat is the perfect energy store, well, for low intensity exercise. We've got so much of it, we take it from our body fat. It's also it's very energy dense. So let's say let's imagine I'm not remotely 10% body fat, but let's say I did have especially low body fat and 10% body fat, and I was an 80 kilo person. So if I was that person, I would have 8 kilos of fat. Now, each gram of fat has 9 calories. So I'll have 8,000 grams of fat, and each of those grams, I'm able to get 9 calories of energy. So if you do the sums, you'll see that even that person who's very low body fat percentage will have over 70,000 calories worth of energy available to perform work. That's a huge amount. So fat is my perfect energy store for low intensity exercise. I'm also able to break down carbohydrate. Carbohydrate is not quite so energy dense, but it's a bit quicker to be able to be released. So that's why under higher intensity exercise, my body starts to burn more carbohydrate. And we see that switch over. It's usually when your body, when your breathing rate starts to increase. So sometimes you use what's called a talk test to see if people can still talk whilst they're exercising. And when people just start to have to sort of take a breath before they speak, we can see that they're using their carbohydrates a little bit more. Their body's starting to work that a little bit harder. They need that quicker access to energy. So the aerobic system is dominant in low intensity exercise, but it also supplements higher intensity exercise. The thing is, we don't switch it off. You see some pictures and, or ideas of people being in fat burning zones and what have you. We never switch off the aerobic system. It just reaches its capacity. So what are the two main fuels? Well, carbohydrate for higher intensity exercise and fat for lower intensity. We might also use a little bit of protein, particularly in exhaustive exercise or under starvation maybe. It can be converted into a sort of carbohydrate basically. So it all takes place in these things called mitochondria. So mitochondria, remember I showed you that picture of the muscle fiber earlier. At a tiny level, mitochondria look like little kidney beans, and they're found deep within the muscle fiber. So you can sort of see the outline there. So tiny little bean-shaped structures that you find inside muscle cells, and they provide all of this processing of those fuels. So that's where aerobic energy is made. So there are three systems. So you're kind of, to recap, think about the fuels and the duration and the use of each of these systems. So if we went ATP PC, what's the fuel? It's creatine phosphate. How long does it last? Up to about 10 seconds. And it's used in high intensity exercise. The lactate system, the fuel is glucose or glycogen, so basically carbohydrate. It's used for up to about a minute and a half of all-out high-intense exercise at a maximum, but can also be used to supplement high-intensity aerobic exercise. Examples of it being used would be things like a 400-meter race or 800-meter race. And then you've got the aerobic system at the end. So that's used almost kind of limitless, really. I mean, its sort of duration is, you can do an ultra marathon. You could not stop. But good examples of its use are things like a marathon, walking, that sort of thing. We use our aerobic system. We have to. That system never stops. So fuels, primarily carbohydrate and fat, a little bit of protein under great stress. So those are the biggies. Hopefully we've gone through enough for you to start thinking about how you can answer your workbooks. So this picture is quite a sort of common sight you'll see to show the distinctions of the different systems. The important thing to look at with this picture is where things start to cross over. This first bit is in 15 seconds. So this next bit is up to a minute, and then from there it goes on from 3 minutes onwards. Now, what we see here is the ATP PC system. So the system is in red. So what you see is here we're using that system, so it absolutely maxes out after about 8 seconds or so. If we keep exercising, if we keep sprinting, to keep going, the lactic acid or the lactate system has to start kicking in. So if you imagine, let's say I was running and I'd been running for about 10 seconds. Now, looking at that, this is my lactate or my creatine phosphate. So here's someone who's running for 10 seconds. So the creatine phosphate system is being heavily used, but I'm also using a little bit of the yellow line. The yellow line is glycolysis. This is the lactate system. So I'll give it its word we've been using. So this is the lactate. So glycolysis is the breakdown of glycogen or glucose. So that's the lactate system. But you'll also see we've got a tiny contribution from this oxidative system at the end. So the oxidative is aerobic. It's hard to write. Aerobic, there we are. Lovely. So when you look at that person who's running, sprinting for that 10 seconds, most of it's creatine phosphate, but there's a little contribution from the lactic acid system, and there's a tiny contribution from the aerobic system. If you contrast that with, say, the first 3 seconds, let's say at this point, you can see it's mostly creatine phosphate system, and there's a tiny contribution from the other two. Let's now look at what happens when we've been running for a minute. So you can see mostly glycolysis, the lactate system, quite a lot from the aerobic system, and not much from that creatine phosphate system. Let's say now I'm working 3 minutes, so that's what, halfway through a 1500 meter race, or well, for someone who's not an elite athlete. So mostly aerobic, a little bit of lactate, and no creatine phosphate. So the systems never switch off completely, but their contribution in different types of exercise will vary. So this table, I'm not going to go through it. I'll leave that for you to pause. I'll go through one, and I'll go through a couple of sections, just so you know what it's banging on about. So this picture here, so let's say the first 4 seconds, it's an anaerobic exercise. The energy is going to be all from ATP that's supplied in muscles. Now, if I keep going, it's still going to be anaerobic, but I'm starting to use that phosphocreatine or that creatine phosphate system. If I keep going, and now I'm doing exercise that lasts 45 to 120 seconds, I'm going to be using mostly my anaerobic system, particularly the lactate system. The fuel is going to be glycogen. But also remember, I'm going to have a little contribution from the aerobic system as well. But if I keep going for much, much longer, the fuel is going to be mostly my aerobic system. So the system is going to be mostly my aerobic. And the fuels are going to be fats and glycogen. So I've tried to get away from looking at things like carbohydrates, fats, and proteins a little bit, to just try and get really sort of nail home the idea that these systems use or are there to create ATP. Our muscle cannot use carbohydrate, fat, or protein. It must be converted into ATP. So all of these systems convert our fuel, our food, into ATP. So if we use carbohydrates, we get enough energy per gram, we create around 4 calories of energy. Fats are much more energy dense. So when we eat a similar quantity of fat, we get far more calories. This is why fats help us put on weight, because it's easier to get that calorie surplus. if we run a calorie surplus, our body will store it as excess energy as fat. Proteins also give us 4 calories per gram. The thing with protein is we don't really have a great store of it. You know, our glycogen stores carbohydrate. Fat stores fat. Muscle is really our body's protein store. So I don't want to be in a race or a workout breaking down my own muscle. That's why our body only tends to use it at quite late stages in events. So this picture is one that you may sort of see this style around. I'm just going to talk you through it quickly and then give you a little bit of an opportunity to complete your workbooks. So let's just run through it briefly. So at the bottom, it talks about intensity. So intensity of exercise. So this end is low, so something like a walk, and this end is really high. So sprinting maximally, or sprinting maybe, or running at a high intensity for a long period of time. Now, as at low intensity, if you look, we've got fat and glucose usage. So when I'm sat here on my behind, probably more than 90% of my total fuel is going to come from fats. I don't need to start using carbohydrate. Now, let's say I start going for a walk and my intensity begins to rise. Now, as I'm walking into town, this is just a normal town. At this point, what I see is now, do you see how glucose has now had to start providing a greater percentage of my total calorie need or my total energy needs? So the higher the intensity, the more glucose we use, the more I need to access that slightly quicker store of energy. So as a percentage, the total amount of fat I'm burning goes down. As a total amount, it just keeps going. It sort of reaches its limit. So by the time I'm working at around 60% of my maximum intensity, so this is probably, still relatively sort of gentle sort of feeling exercise, but now let's say I've broken into a very light jog. So now my fat and carbohydrate needs are or usage is pretty matched. If I keep increasing that exercise intensity, so now if I keep increasing that exercise intensity, what you start to see is that what we've got is what you can start to see is as that exercise intensity increases, the amount or the percentage of glucose I begin to use starts to increase. So the total amount of fat has sort of stayed relatively similar, but as a percentage of my total usage, carbohydrate becomes much more dominant. So I start to really rip through my carbohydrate stores at those higher intensities of exercise. So when I'm at my almost at my maximal, my fat burning capacity has almost kind of reached a peak, and I keep drawing on my glucose stores. I keep having to burn my carbohydrate. I even start to work anaerobically. So, to recap, at low intensities, the dominant fuel for the aerobic system is fat. As exercise intensity increases, we need to burn glucose or glycogen to meet our energy needs, as it's quicker to break down. At higher intensity, the ability to break down fat reaches its maximal capacity. So it doesn't stop. Sometimes people think this picture shows it's sort of stopping. Yeah, it just reaches its maximum capacity. So if we want to exercise more intensely, we start supplementing with anaerobic breakdown of yet more glucose. So I've got a little note on the bottom to say that this graph shows a percentage of fuels used, not total amounts. So as we start increasing our exercise intensity, we don't burn less fat. It just, as a total contribution of all our energy usage, it becomes relatively less. So this is just a quick pause now. This is to fill out your workbook. So what I want you to think of, so you're asked to describe how carbohydrates, fats and proteins are used in the production of ATP. So I've just kind of given a little outline, and again, just pause this presentation when you come to it. So I think it's a difficult question, actually. I would start by sort of showing that you understand the concept of energy systems. So begin by just sort of stating your bodies only have 2 to 3 seconds worth of stored ATP. And this means that when that's used up, we have to resynthesize it, i.e. remake ATP. I should say if we are to continue exercising. So the first of our body's systems, or the first system we draw on, is our ATP PC system. I think sometimes it's almost a little bit confusing to almost have this idea that we first use that system. I'm not sure that's really the case. Is if I I'm sat on my behind, as I've said, if I go for a walk, I don't start using my ATP PC system. My aerobic system has got it all covered. In the same way, if even in something like if I'm jogging, let's say I've gone to a park run, I start jogging, that first 10 seconds of a jog, it's just going to be aerobic. So in high intensity exercise, that ATP PC system is used for that first burst of activity. We use that system in high intensity exercise for short bursts up to 10 seconds of maximal output. So it doesn't use carbohydrate, fats or protein, it doesn't use any of them. But, and this is worth mentioning, because if I ran, you see it, let's say if I did a 100-meter sprint, let's say you caught me at the finish line, I wouldn't want to imagine how long it takes me these days. It's quite a significant time, I'd think. But let's say you caught me immediately on that finish line. Now, if you sort of started interviewing me and talking to me, you'd see me really heaving for breath. I've just done 10 seconds all out activity. Now, most of my energy has been provided by the ATP PC system. What was the waste product? Well, there wasn't one. A little bit will be from my lactic acid or my lactate system. Probably not enough to start accumulating enough lactic acid to cause me to stop running. So actually, I'll be really heaving for breath. So a little bit of that extra breath, that extra aerobic work is about getting rid of that lactic acid, but also a lot of it is about restoring those creatine phosphate stores. So I think it's really important to show we don't use it. We don't use those fuels in our ATP PC system, but we do use them to recover that system. So if I sort of, let's say I was looking to lose weight, I could go on these long, slow duration runs, try and burn a little bit of fat, or I could work really hard using these bursts of activity that I enjoy, that I can get into a short space of time, in the knowledge that I'm still burning that fuel to repay that ATP PC system. So point number 4, the lactate system is the system we use for high intensity, longer duration exercise. It uses glucose or glycogen, which is broken down without oxygen. So your task is to explain what the byproduct is and how it affects us. You might also mention that the byproduct is there, and we often just deal with it. It's only when it starts to accumulate that lactic acid becomes a problem in our body. You might also mention that the lactic acid system is quite inefficient, that if I burn glucose with my aerobic system, I get around 38 molecules of ATP. If I burn it in my lactate system, I get about 2. And then lastly, you're going to explain the aerobic system. So the aerobic system uses all of those fuels, carbohydrates, fat, and protein. And depending on the intensity, sorry. So you could show that carbohydrate is used at higher intensity aerobic exercise. Fat is used at very low intensity exercise. And the contribution of carbohydrate increases the higher the intensity. So that's a nice little plan for that task on page 30 of the paper workbook. So it might be a good idea now to just take your time and go and either complete a plan or actually write directly into your workbook. So this table just covers the key features of each of these systems. So it's just a nice one to sort of just reacquaint with, just because it sort of shows the key bits that I think we should all know. So so we've got the creatine phosphate on the left-hand side. It's anaerobic, it's quick, provides a chemical energy. So the creatine phosphate, it's very limited amount of ATP. Great thing is there's no waste products, really short duration. We use it in high intensity exercise. So this idea that we phase it in is not really true. We use it when we exercise hard. We can recover quite quickly from it, depends on what other processes our body's doing. Our lactate system, again, it's an anaerobic one, a bit like the creatine phosphate system. It's quick. We use glycogen or glucose. It produces a limited amount of ATP. And the important thing, the waste product is lactic acid. So up to 2 minutes, it says here, of intense activity. It really depends on the contribution of the aerobic system. So the fitter we are, the more our aerobic system almost kind of backs up that lactic acid system. So if I went out for a 400-meter run now, I would probably be using a large contribution of my lactic acid system. I would feel awful at the end of it. If I ran consistently and let's say trained for 3 months, 4 months, I would start to get better at using my aerobic system at higher intensities. So it's used in high intensity, up to 60 to 90% of your maximum. And it's in exercises that, it's a funny little thing actually. You can recover from it quite quick, but high intensity exercise where you create lactic acid, there still tends to be a little bit, complete clearance of lactic acid can take a little while. So this is why race pacing is really important. So in something like a marathon, if you get out of the blocks and accumulate lots of lactic acid in the first few miles, it's very difficult to wrestle that back. There'll always be an underlying amount in your muscles. So in the aerobic system, it is aerobic. It's very slow. The fuels are glycogen and fat and a little bit of protein under sort of starvation or exhaustion. We're pretty unlimited in the amount of ATP that we can generate. There's no fatiguing waste products. In something like a marathon, a little bit of a limitation is even just muscle damage. You know, muscles get tired. But also, if you push too hard, then your lactic acid starts to be used. It's used for very low intensity exercise, but again, if you want to go faster, harder, you can get fitter. So your aerobic system provides energy at higher intensities, and you start to use your lactic acid system to supplement it. So the last task I'm going to leave you with, this is on page 31 of your workbooks. And what you're asked to do, I'm just going to talk you through what's required. So you've got a table, 7.2, and it on the left-hand side, it lists the energy system. So creatine phosphate, lactate system, anaerobic system. So each of those systems, you're asked to describe their use during aerobic exercise and during anaerobic exercise. It's a very vague question, actually, and you might need to just do a little bit of extra explaining. So here, the creatine phosphate used during aerobic exercise, well, it doesn't really get used during aerobic exercise, does it? Because remember, the creatine phosphate system is used in high intensity exercise that's at about 95 to 100% of our all-out effort. So just to say something, I've put actually, it could be used at the start of a race, such as a rower getting up to speed. It could be in something like a 1500 meter race where sometimes they get out of the block pretty quick. So you could use it in literally the first 4 seconds to just get down the track in front of your opponent. But otherwise, in something like a real classic aerobic run, you're not going to use it. Now, what I'm leaving blank is this bit on the right-hand side, because I want you to think about how you can explain the use of the creatine phosphate system during anaerobic exercise. Now, one of the key figures in your book is this idea that we use it when we work at about 95%. My pen's not working. 95% of maximal effort or higher. So you're going to need to reference that to say we use it during anaerobic exercise in really high intensity situations where we're working at 95% or higher. We might use it in something like a sprint start. We might use it for most of a 100-meter race. So I want you to give your ideas to explain how that system's used. So the lactate system, very little use in low pace activities, but it can be used to supplement higher pace activities. So something like a 1500 meter race, very aerobic, but actually you're not going to do it all aerobically. You need to work at the right pace. You're going to need to supplement your running with that lactic acid system. In the same way on here, that it's going to dominate in many anaerobic activities lasting up to 1.5 minutes of maximal or very high intensity exercise. And you can give some examples about the sort of activities that's going to mean. So I've put here it can be used without impeding performance for some time. So something like a fast sort of tempo run that you might be maintaining for 20 minutes, the body's creating a little bit of lactic acid in the background. But if it's not accumulating, it's not going to massively impact your performance. It might only be near the end of the run where you start to really notice the effects. So I've put at higher intensities, lactic acid might start to accumulate. And then lastly, the aerobic system, I've said can be solely used during low pace activities. For higher paced activities, so something like a 1500 meter race, it might need supplementing by the lactic acid system to achieve the desired pace. You might also mention about how at really low intensities. Fats are the dominant energy source or dominant fuel. And as we get higher intensity, glucose becomes more important. So your job is to complete this. So hopefully you've got a bit of a better grasp of energy systems. I think the key thing that I was trying to get through was this concept of the body's energy currency, that carbohydrates, fats, and proteins are used in the production of ATP. So we don't just directly use them, we have to convert them to this substance called ATP. We've had a look at those three energy systems. We've seen that the ATP, or the creatine phosphate system, is used in really high intensity exercise. We saw that the lactic acid system is used across a broad range of higher intensity exercise, and the aerobic system is mostly low intensity. We had a look at the fuels, and we also considered the mechanisms of fatigue of each of those systems. So, hopefully you found that useful, and hopefully you've now completed that relevant section of your workbook. So, thank you very much.